Alright everybody, it is evening time in my world, so I'm sorry if you hear my dog eating in the background. He's finishing his dinner. Okay, getting on to inverse trig integration. These are essentially go along with our inverse trig derivatives, right? It's just the same thing but backwards. But here, right, we have some constant a as well that's going to be coming into play. Notice for arctangent and arcsecant, there is a 1 over a out front involved as well, but not for arcsine. Magical, magical, magical. Okay, so these are our derivatives. These are the things that we're going to be looking for. These are the patterns that I'm going to be looking for. Also, I do not want anything here other than just like an x or something, so we're going to be using U substitution to do some of these things as well. Okay, so let's just get after it. So evaluate each of the following indefinite intervals. So in this case, there's a few different ways that you could do this. You could let x be, or sorry, u be 2x, but the way that I prefer to see this, again, I want this to just be a variable squared or something like that. So, like I said, you could look at this as 2x squared, and I could let u be 2x, so that that would be a 4 minus u squared, and then a would be 4. We could do it that way. That's fine to do it that way. But the way that I prefer to see this, and this is a little bit easier, is what I can do is I can factor out the 4, because really all that this represents is 4 times 1 minus x squared, which is straight up arcsine. And that means that I can rewrite this integral as 1 over 2 root 1 minus x squared dx. Don't forget the dx, please. Pay attention to the notation on all this stuff. It's really tedious, but it needs to be done. So I can factor out that 1/2. Then I have the integral of 1 minus x squared dx, and then there is my arcsine. So 1/2 arcsine of x over 1, so just x, plus c. Don't forget that plus c there as well. All right, moving on. So here's one that's a little bit more involved. Oh yeah, good times. So I would rewrite this to help me see the u a little bit easier. Once you get into these things, it will be easier to see the u anyways. But for now, I'm going to rewrite it the first few times for you. So I would have 1 over, really 4, just remember that that would be 2 squared plus 3x squared dx. So off to the side here, I'm going to let u be 3x. Then du is 3 dx. And I don't have a 3, so what I need to do is du over 3 is dx. So I have 12 over 3, the integral of 1 over 4 plus u squared du. Right, and 1 over a squared plus u squared, right here, 1 over a squared plus u squared is 1 over a arctangent of u over a plus c. So I have 4, right, so that's just 12 divided by 3, times 1 over 2 arctan of u over 2 plus c. I can distribute that 4 to make this 2 arctan of u over 2, which would be 3x over 2 plus c. The 4 can multiply into the c, and that's fine. You could write it as 4c, but it's just some constant that's unknown, so it's just 4 times as big as that c already was. Okay, and that's it. All right, this one's a little bit interesting. I kind of like it, but it's really easy to see the u. So if I let u be cosine of x, then du would be negative sine of x dx. So really all I need to do is something with that negative up front. So I'm going to move it over, make that a positive, so that's a negative du. So this comes out negative the integral of 1 over 7 plus u squared du. So then notice, this is still a squared. All right, so this is still going to come out as arctangent, but it's going to be negative 1 over root 7 arctan of u over root 7, which u was cosine of x, over root 7 plus c. And that would be my answer right there. So these really should be pretty straightforward once you get the rules down. Some like this are going to be a little bit trickier, but what I would like you to do is break this up, because what I can do here is say that this is t over t squared plus 16 dt minus 4, the integral of 1 over t squared plus 16 dt, right? Because then the second one, this is just arctan right there. 1/4 arctan of, what, t over 4? And then this first one, I can do u substitution with that part. That's the reason that I would like to break those up. So I'm going to let u be all of t squared plus 16, so that means du is 2t dt. I can divide over that 2. Let's make this 1/2. Quiet, Cora. I'll kill you. Is it bad that I threaten my dogs' lives all the time? I don't think they understand. So this would be 1/2 the integral of 1 over u du minus 4 times 1/4 arctan of t over 4 plus c. And 1 over u is ln, right? So 1/2 ln absolute value of t squared plus 16. And really, I don't need the absolute value in this case. Minus arctan of t over 4. All right, so again, really all this is just using those derivative rules, but we're using them backwards with our inverse derivatives. Okay, this one's going to require a little bit more effort, because what I would really like to happen is I wish that I could let u equal the entire denominator on the inside of that square root. That would be wonderful if we could do that and have it work out. And it almost does, right? We have that x up here, but it doesn't quite work out. But I have negative 2 times x plus 2 dx. So it's almost there, but it's really not quite. However, what I could do to make it be there is I can relook at this as x plus 2, and then I have a plus 4 out there. So if I break up these integrals like that, shut it, Cora. All right, so take a second, make sure you agree that that's the same thing. All right, so x plus 2 and x plus 4, or not x plus 4, but just plus 4. Right, so I factored out the 4 as well. Because that second one, that becomes just an arc sine, where I can let my u be x plus 2, but then du is just dx, so there's no reason to really do that in this case. And then the first one, I can actually use my u substitution that I wanted to. So this becomes the integral, but it would be negative 1/2 because that negative 2 is not there. All right, so I need to divide it over with the du of 1 over root u du, which becomes much easier, right? And then plus my 4 arc sine of x plus 2 over 4 plus c. So now I just need to do the integral of the first part and replace my u. So this would be negative root u, so square root of 16 minus x plus 2 squared plus 4 arc sine x plus 2 over 4 plus c. And there we go. And that would be it. Alrighty, moving on. What do we do with u? So let's see, that's not really a natural log one. Can't break it up. So you guys don't know about partial fractions yet. So what we could do, check this out, is you can remember something from Algebra 2, and a little bit of calculus, or pre-cal, is I can re-look at this like that. Don't forget your dx. Right? So again, this is still the exact same thing. I haven't changed anything. But this allows me to essentially make a perfect square term when I factor it. And there's our tangent. Right? Because I could let u be x plus 2 here. U would be that. Then du would just be dx. So this is u squared plus 9. So this would be 1/3 arctangent of x plus 2 over 3 plus c. So sometimes completing the square can be of use. Again, if you're not as comfortable with those rules, that's fine. You'll get more comfortable with them through practice. So just keep practicing them. Biggest thing to remember, and don't mess it up, is that this is a squared right there. So when I put in 1 over a, and this divided by a, right, that a is just 3. Okay. Here, right, same idea. So this is a good time to take a pause of the video, try it out for yourself, see what you come up with. Here we go. So the integral of 1 over, let's see, I would want this to be a plus 4 plus 3, so that it comes out as x minus 2 squared plus 3 dx. So this is 1 over root 3 arctan of x minus 2 over root 3 plus c. And that's it. All right. This one's a little bit more annoying, but still not horrible. It's just going to change how I want to look at it. And I think this is our last one. Hey, look at that. Yeah. Okay, so similar to that other one, it would be lovely if I could let u be that entire denominator. And I almost can, right? But I just want 2x plus 2 up there. So if I can re-look at how I want this to be 2x plus 2, but it still has to be the same numeric value, so that must have been a minus 7. So let's break it up into those, because then this first part, I can just use u substitution. The second part, maybe I can complete the square and it's arctangent or something. I did want a 7 there. 7. Okay, so I'm going to split this up into 2 different integrals, and I'm going to use the u substitution that I have annotated already. Right, and it is 2x plus 2, so this really is just 1 over u du. Then I have minus 7, the integral of 1 over x squared plus 2x plus 2 dx. So this is natural log of u. I do need the absolute value here. Shut it, core. Hope you die. Die. Just down here begging for something. Dogs these days. Don't they have like fingers and thumbs and they can just get whatever they want? Haven't they evolved yet? No, probably not. Okay, so now let's change how we look at this, right? It would be nice if I had a u squared plus a squared, so really with that 2x term, I just need a plus 1 to make that a perfect square. So I better look at that plus 2 as a plus 1, such that this turns into integral. That's super ugly, I'm sorry. 7. All right, so now I'm going to have an arctangent. So ln absolute value, x squared plus 2x plus 2 minus 7 arctangent of x plus 1 over 1, really. So just x plus 1 plus c. Easy money. I think you could do plus 7 arc cotangent. And I know up here I have listed If it's negative, it comes out as arc cotangent. If it's negative, it comes out as arc secant, or arc cosecant and cosine. But I really rarely see those used. Even when I typed, which one was it? This one here that I made up. When I type that into engines that I use to check integrals and make sure I've done it correct before I teach it sometimes, they actually spit out arc tangent, and I'll have to verify this again, but I don't think that it's really going to come out. Even in searching it, being like, when do you use arc cotangent after an integral? I'm not finding much information. So don't worry too much about those negative parts. I would just worry about the ones that I have listed. Other than that, that's all I can think of right now, and I will talk to you guys soon. Bye.